In this video, we're going to learn about the periodic table. Now, the periodic table is divided into horizontal rows called periods and vertical columns called groups. Another way that we can divide the periodic table is into the metals, nonmetals, and metalloids. Metals are lower and further to the left on the periodic table, and most elements are metals, as you can see. They're the blue ones. Non-metals are in yellow. They are further to the right and up. And in between them, there's this sort of staircase of metalloids. Exception, of course, is that hydrogen is a non-metal, and it's the top left. But in terms of physical properties, metals, they are solids always. They're ductile, which means that they can be drawn into wire. They have a metallic luster, or they're shiny. They're malleable, meaning that you can hit them with a hammer and they'll sort of bend into shape. Think of what blacksmiths do. And they're good conductors of both heat and electricity. That's why they're used in wires. Non-metals are just not metals. So they're going to be dull, not shiny. They're going to be brittle. If you hit them with a hammer, they'll shatter. And they are the opposite of conductive. They are insulators in terms of insulation of heat and electricity. They can be found in the solid phase, but they also can be liquids and gases. And metalloids are somewhere in between in terms of their physical properties. I'm actually just going to show you, going down this one group, the fifth group, nitrogen and down, we've got nitrogen is very, very much a non-metal. It's a gas. As you go down from nitrogen to phosphorus, it's a little bit less non-metallic in the sense that, well, at least it's a solid, but it's not shiny or anything. Arsenic and antimony are metalloids, and arsenic, you can look at it, it's a little bit shinier, and antimony shinier still. I bet if you were to hit arsenic with a hammer, it would break pretty easily. Antimony might be a little bit bendy. And then below that, we have a full-on metal, which is bismuth. And that definitely is going to be malleable and it's definitely shinier. So as you go further down and further to the left, something is going to be more metallic, and the most non-metallic elements are further to the right and up on the periodic table towards that corner. So I've talked about physical properties. In terms of chemical properties, very, very simple. Metals lose electrons. Non-metals gain electrons. The group 8 non-metals notwithstanding, but more on that in a bit. Next, we have diatomic elements, which exist naturally only in pairs. So we have Br2, I2, N2, Cl2, H2, O2, and F2. And if you say this out, you will hear Brinkelhoff, which people tend to remember. Another way of memorizing these diatomics is that it's a 7-7-7 rule. If we look at the number of them, there are 7 among them. There are 7 diatomic elements. And if you go to element number 7, which is nitrogen, and make the number 7, if I sort of trace that out, those are the diatomics, except for, well, hydrogen also is included. So 2 ways to memorize them. And David Hasselhoff tells you that the Brinkelhoff elements, they exist in pairs only as pure elements. If you form a compound that involves bromine or iodine or nitrogen and something else, then you might not have pairs. So for example, CH4 exists and NCl3 exists. Just because there's nitrogen and chlorine in these doesn't mean that you need to have them in pairs. The diatomics exist only as elements in pairs. So thank you, Mr. Hasselhoff, for that. All right. Next, I want to go into the radioactive elements, the elements that exist with no stable isotopes. They are technetium, number 43, promethium, number 61, and then anything bigger than lead. So 83 bismuth and up from there, they're all going to be radioactive. Actinium should actually be shaded as yellow. So that's a fairly easy thing to remember, just 43, 61, and then anything bigger than lead. is going to be radioactive with no stable isotopes. Bismuth is mostly safe, so before you throw away your Pepto-Bismol, there is one isotope, bismuth 209, that is very, very close to being stable. It has a half-life of nearly forever, and that's basically all the bismuth you'll ever see. So it is no more dangerous than eating bananas, which have a slight radioactivity from the potassium. Moving on, there are synthetic elements that only exist as human-made elements, and they are technetium and promethium, which we already mentioned in the previous slide, these two. And then anything 93 and up. So I know you've seen 83 to 92 as being radioactive, and that's true, but they do occur naturally. You can go to mines and actually mine like uranium, for example. Even elements like astatine and francium that exist in tiny, tiny quantities naturally, only a few grams in the universe at any given moment, they do come from bigger elements like uranium, decaying down through them and past them to the stable lead. So just remember that it's neptunium that is the beginning of the synthetic elements. You can only really make neptunium. You'll never see it in nature. That being said, plutonium, useful for nuclear fission, used in nuclear bombs. Americium is in your smoke detectors at home, for example. So just because they're synthetic and not common, at least naturally, right? They doesn't mean that they aren't useful to us. Some of them are quite useful. So that's the synthetic elements. Moving on to some of the main groups. So the group 1 elements, these ones right here, they are the alkali metals. They are very, very much metallic, meaning that they're super, super soft, and they're super, super reactive. You can cut most of them, actually you can cut all of these with a butter knife. And their valence electron configuration is S1. So lithium, its last part of its electron configuration is 2s1, sodium is 3s1, potassium is 4s1, etc., etc. These are super, super reactive. They will explode on contact with water. Group 2 are the alkaline earth metals, and they are the next one over. They are still quite metallic, but they're not quite as soft as the alkali metals. They're not quite as reactive, though pretty reactive. You throw them in water, they'll react, but very slowly for the most part. Like barium, you'll get a pretty decent reaction. All the way up to calcium, you will. Magnesium will very slowly oxidize, reacting with water. And their electron configuration in the valence shell is S2. So beryllium ends in 2s2, magnesium in 3s2, and so on and so forth. Radium, by the way, is radioactive, which is why it has its name. Then we're going to talk about the D block, which we're just going to talk about all in one piece, even though there are many groups here. These are definitely a lot less metallic, even though they consist of many metals that you're familiar with, like iron, nickel, and so on and so forth. They're much less reactive than the group 1 and group 2 elements. Even among them are some noble metals like gold and platinum, which will not react with almost anything. That's why gold and platinum, in addition to being rare, they make very good jewelry because you never need to polish them. They never oxidize. They're right here. Palladium also is very, very non-reactive. They have a range of valence electron configurations since they are in different groups. In general, we can say that they will lose their s electrons first, and they tend towards having a D5 and a D10 electron configuration when they ionize. So, for example, scandium can lose its two valence electrons, its two s electrons first, and maybe also its d electron. When we get over to, say, zinc, for example, zinc is actually very stable in the positive 2 state, where it has an electron configuration of D10, 3D10, where the two 4s electrons have been lost. Moving on, we've got the halogens. They are very, very much non-metallic. They're group 7 right here. And they include solids, liquids, and gases. So fluorine and chlorine are in the gaseous phase, but as we go further down, bromine, which is right here, bromine is a liquid, iodine is a solid, and these are very reactive elements. The further up they get, the more easily they gain electrons, and generally they gain electrons pretty easily. And their valence electron configuration, because they have 7 valence electrons, is going to be s2p5. So 2s2, 2p5, 3s2, 3p5, etc. Moving over to group 8, we have the noble gases, which are all gases. We got helium, neon, argon, krypton, and xenon. And neon lights, actually, yes, they could be neon if they have this red color, but also argon and krypton and xenon. Xenon actually is used in a lot of car headlights, and you might look at them and see a slight purple color. That's because of the xenon gas. In general, they are chemically inert, and they have a valence electron configuration of s2p6. And so that is all for the main groups and the periodic table. I hope this video has been helpful. Feel free to leave any questions or comments in the comment section below, and thanks for watching.